Hello, this is Dr. Jack Jackson. In this video, we're going to be talking a little bit about the dot product of two vectors. So in the previous video, we talked about a scalar multiple, which was a scalar times a vector, and the answer was a vector. In this video, we'll talk about the dot product, which is a vector times a vector dot vector, which is a scalar. And in the following video, we'll talk about the cross product, which is defined for 3D vectors, and it's a vector across a vector is a vector. So there are three different kinds of multiplication involving vectors. Okay, um, so notice that we use sort of three different symbols for them. If a scalar, a real number, is just written next to a vector, that's how we usually indicate a scalar multiple. And then we use these two different multiplication symbols, the raised dot and the cross, for the two different kinds of products for a vector times a vector. And so we name them by the symbols, the dot product and the cross product. Sometimes people call the dot product a scalar product because the result is a scalar. I don't particularly like that because I think it's a little confusing when they might confuse that with the scalar multiple, which involves a scalar times a vector, giving a vector output. So I prefer not to use that. Another time, some people will say a dot product is called an inner product, but we're going to call it a dot product, which is probably the most common. And just like we did with the scalar multiple, we're going to present an algebraic definition first, explore it with GeoGebra, and then find the geometric interpretation, and then finally prove that it's equivalent to the algebraic definition. But once again, remember this is kind of backwards. It's not because somebody said, oh, let's find a cool way to multiply two vectors. And then what does that happen to turn out to be algebraically? No, it's actually more the other way around. People said, oh, I need something that does this, like in the case of the scalar multiple. I need something that scales or stretches a vector. Well, how do you accomplish that? Okay, and then what does that turn out to be algebraically? Same kind of thing happened for the cross product. They actually needed it for its geometric interpretation, which actually came first, and then the algebraic definition came second. But we're going to actually teach it backwards. Okay, so it actually turns out it's pretty simple formula for getting the dot product of two vectors. So first of all, it's defined for any dimension vector as long as the two vectors have the same dimension. So you can do the dot product of two 2D vectors or a dot product of two 3D vectors. It doesn't make sense to do a dot product of a 2D vector and a 4D vector. They have to have the same dimension. But when you do that, say you have a vector A that's given by components A1, A2, A3 up to some AN, and vector B given by components say B1, B2, B3 up to Bn, then that is the dot product is you just multiply the corresponding components and then add them all up. So you take A1 times B1 plus A2 times B2 plus A3 times B3 and so forth, ending with AN times Bn. Or in summation notation, it's the summation from k equals 1 to n of A sub k times B sub k. So here's an example. If you take the two 3D vectors here, do the dot product, we have the vector 1, 2, 4 dot with vector 2, negative 3, 5. And so we just do it like this, 1 times 2 plus 2 times negative 3 plus 4 times 5. 1 times 2 is 2, 2 times negative 3 is negative 6, 4 times 5 is 20, and if you add those together, you get 16. Notice that the answer, once again, is a scalar. The most important thing of all that you need to know about these three products is what they are, right? Whether the answer is a vector or a scalar. That's going to be the first thing you need to be sure that you understand. And if you see this is a really, really easy, straightforward way to actually multiply these together. Seems reasonable to do. But what's it for? What does it do? What does it do for us? Okay, so we got this cool way of multiplying vectors, but what does this scalar tell us? And so we're going to investigate that by looking at a couple of GeoGebra applets. Here's one that Tim Brzezinski put together. He does a lot of really good GeoGebra things. Here's a screenshot from it, but let's take a look at it. So as I do this, the idea is to get into this, hopefully get into this yourself, and play around with this, and you'll see me do that a little bit here. And see if you can figure out something about this. Now, of course, when you do this, up here at the top, you're going to see two vectors generated, and you'll see their product here. They're generated by controlling these positions of these 3 points. Vector v goes from this point to this point, which with the scale is 1 here in both directions. And so this vector goes, this one goes to the right 3 and up 3, so that's the second vector. The first vector is here, goes to the right 2 and up or down 0. That can be changed dynamically. You'll see the algebra worked out here, or arithmetic, whatever you want to call it, worked out up here for the dot product. But then you'll also see an angle represented here, and we're going to experiment with this to see if we can get some kind of feeling for what happens. We'll see if we see any patterns, make some conjectures, and maybe test those out. So let's go ahead and get into that with going to this this here, and he has a little video using this as well, and there's the app up there, but I like to go to these 3 dots up here and open in the app, and so I'm going to look at that. Okay, so here we go. Here's a vector, and let's look at a couple of different ones. So see if you can get any kinds here. This is 48, just to check it out. So that notice that this vector, let's do this one here. This vector v goes to the right 1, 2, 3, 4, 5, 6, 7, 8, and down 1. So that's 8, -1. This vector goes 1, 2, 3, 4, 5, 6 to the right and up 2. So that's the vector 6, 2. We can see the dot product computed here. 6 times 8 is 48. And 2 times -1 is -2. 48 minus 2 is 46. And so there's 46. Here's the angle between the vectors. The program can measure that for us. Okay, so I'm just going to move some things around and see if you notice anything. Oh, look at that. The dot product is 0 right now. And look at the angle there. Oh, it's still staying 0. Okay, what if I go this way? Are you seeing any patterns yet? It kind of helps that he did some color coding here. Oh, look at that. Now the dot product is negative. Do you see any relationship between, say, the angle and the sign of that dot product? Now remember, we're just computing the dot product by the definition, but we're also seeing the angle here. And if you notice that when the angle's red, we have a -1. When the angle's black, we have 0. And the angle is green, when the marking on the angle is green, we get a positive product. Okay, now notice this, also a couple other things. So what did you notice? Okay, hopefully you notice that when the angle is acute between 0 and pi over 2, or between 0 degrees and 90 degrees, you're going to get a positive dot product. And when that angle is bigger, obtuse, you're going to get a negative. So in other words, when these are sort of pointing more in the same general direction, you get a positive. When they're pointing sort of more against each other, then you get a negative dot product. And when they're completely perpendicular to each other, a 0. Well, maybe that's just because that's a 0 and that's a 0. Let's see. Is it still true for a right angle? Let's see if we can make some other kind of right angle. Where could I put it? Maybe oh, there we go. Hey, sure enough, now the angle is still a right angle, and the dot product is still 0, even though they're not, none of the components are 0. Okay. Now let's look at something here where we fix the angle between them. Look what happens if we make this shorter. Right now it's 4. Well, let's look at it this way. First of all, this one only has an x component or an I component. Okay, and so that that y or j component of 0 means this number right here is irrelevant. It's only going to be the x component of this, the part that's going right along here, not the part that's going up, that's going to affect this one. And if you look, it's just that times the length of this vector. So this vector is actually 7 long, and this one is just the x component going in this way, 4 times that 7 is 28, right? Because that 0 times the second component is going to not add anything to that. So, but the main thing is, notice that the longer this gets, the bigger the dot product is going to be. Okay, so let's go back to our slides a bit. And so based on our exploration, can you answer the following question? Does the order of the two vectors make a difference? In other words, is the dot product commutative? When is the dot product equal to 0? When is the dot product positive? When is the dot product negative? If the two vectors are in the same direction, how does the dot product compare to the magnitudes of the two vectors? Okay, we didn't investigate that one, so let's go back and look at that a minute. And then the other question is, what if they're in opposite directions? So going back here again. Let's see, I've already got it open here. Okay, what if I put them in the same direction? Well, they'll do an easy one first. Here it's only the x components that matter. So 12 times 5 is 60, and that's the length here. But what if I do, let's see, let's go right 3 and up, right 4 and up 3. Okay, we know the magnitude there is 5, right? Just from the Pythagorean Theorem, 3, 4, 5, right triangle there. And let's do this one. Let's go another 4 right and up 3 more. Okay, so that one's twice as long, right? So that one is magnitude 10. And look how big the product is. It's the product of those two magnitudes. Now what happens if I make it go the opposite direction? Let's see, let's go, say, 4 left and down 3. Now they're pointing exactly opposite. Hey, look, once again, it's the size of this one at 10 and the size of this one at 5 multiplied together, but since they point opposite, it's going to be negative. Okay. So again, let's see if we can answer some of these questions now. So first of all, the dot product is commutative. And it's pretty easy to see. If you switch the order of these two vectors, then this dot product is b1a1 plus b2a2 plus b3a3 and so forth. And since these can be reversed, if this is b1 times a1, that's the same as a1 times b1. So since at this level, this is just multiplication of real numbers. Since that is commutative, the multiplication of these, this dot product is easily seen to be commutative as well. Well, when is the dot product equal to 0? It appeared from what we saw that the dot product is equal to 0 when the vectors are perpendicular. And that's actually true all the time. And the dot product is positive when the two vectors are closer to pointing in the same direction than they are to opposite directions, or in other words, when the angle between them is acute or 0. Okay? That is when the angle is less than a right angle, less than pi over 2 radians, less than 90 degrees. When is the dot product negative? Well, it's negative when the two vectors point more in the opposite direction of each other than they do in the same direction. In other words, when the angle is obtuse or a straight angle. If the two vectors are in the same direction, how does the dot product compare to the magnitudes of the two vectors? Well, at least the examples we looked at, if the vectors are in exactly the same direction, then the dot product is just the product of their magnitudes, a positive number. If the two vectors are in opposite direction, how did the dot product compare the magnitudes of the two original vectors? Well, if they're in exactly opposite directions, then the dot product is just -1 times the product of their magnitudes. So if they're parallel, the same direction or opposite, the absolute value of the dot product is just multiply the two magnitudes. But if they point the same direction, then that's positive, and if they point the opposite direction, that's negative. Let's investigate this some more. This time we're going to use another GeoGebra applet. This is one that I made. There's the link to it there. You might go ahead and if you have my link where you can click on it, that's fine. If not, might type that in your web browser. And when this comes up, it looks something like this. It may look a little different when it first comes up, but down here at the bottom, there should be a bottom for magnitude and direction example and a component example. If you click on component example, an example here, some information shows up here and one comes up there where you control components. Very similar to the way we did the last one, but they don't necessarily have to be integer components. Or we can do this one, magnitude and direction example. For right now, that's what I want to click on and deselect the component example. One thing about this is now once you have this, you can control the magnitude and direction of each of these vectors by the sliders or these entry boxes. Now it will figure out the components, okay, as by using our basic conversion, okay, and it will, for example, the x component is r cosine of theta. So it's, in this case, it's 8 times cosine of that many radians. And comma, the y component is r times the sine of that same angle. So at least approximately, this is worked out here into x and y components, same way for the other vector. And of course, once you have them in component form, then you can do the dot product. At least approximately, you have it here. So multiply the two x components, the two y components, and add them up, and you get approximately this right here. Okay, and I factored out this 8 there as well. You'll see a reason for that in a minute. So let's get into that one and take a look at it. And actually, we're already in the showing the app version. Okay, so I've got this. So let's kind of take a look at this. So once again, just notice that you can take that one. Notice I'm not changing the magnitude. The end is staying on that same circle there as I rotate it around from 0 to 2 pi. And this is the approximate x and y components. And then the same way for the other one. Or I can leave the angle the same and see what happens as we change the magnitude. So this is going to allow us to investigate some things. So the final right down here. You can see it. There's the number for the dot product, at least approximately. So let's do this. Let's make this one, let's say go out 4. Let's start with an angle of 0. And look what happens again if I also make this the same angle, 0. From what we saw before, this should end up being just 4 times 8, and sure enough it is. Okay, or if I put it at any angle we want, let's see if I can put that there. Let's see if I can get this one to the same. Well, I don't even have to, I can type in an angle, right? So for example, if I want to go to, say, 30 degrees or pi over 6 for that angle, I can type that in. Okay, and I can do the same angle here, pi over 6. So I can put any angle I want, but at the moment I want it to be the same angle. Well, look at the two magnitudes, 8 and 4. Sure enough, we still get 32 here. What if I change the length of this? Now it's 12 and 4. it's still 48, and they're going the same angle. They're going the same direction. What if I make this, what if I go all the way around the opposite direction? So what would be the opposite direction from that? You could add pi to it. So that'd be 7 pi over 6, right? I think that makes it, yeah, that makes it point the opposite direction. So the angle between them is, if you look at it, should be pi, about 3.14. Okay. And what is the dot product now? Well, it's negative 48, 12 times 4. If I change the length there to 8 times 12, it's 96, but they're opposite, so that's negative 96. So that seems to jive with what we had earlier. What if I take pi over 6 and add pi over 2 to it? Let's see, we need to get a common denominator of 6, so pi over 2 is 3 pi over 6, plus 1 pi over 6 is 5 pi over 6, no, I did something wrong, see. 3 pi over 6 plus 1 is 4 pi over 6, or I guess 2 pi over 3 would be reduced. There we go, that's a right angle. You can tell I got it there with it squared off. And, oh, look at that. Dot product is 0, just like we predicted from before. So let's think about this here. So it has something to do, if we keep the, so when is this the biggest? Let's leave the, let's just leave the purple one fixed and move the red one around a little bit. So look at the number here. Let's start here. We had 12 times 8 was 96. That was when they were going in the same direction. What if it's close to the same direction but not quite the same? Okay, there's our 96. Oh, look at it. It's 95 point something now. It's gone down. We haven't changed the lengths of them, just the angle between. And so if you look at the angle between, it's gone down a little bit. Okay, I'm going at more, now it's going back up, closer to the, closer to where they're the same. Where it's the same, it got up to 96. Okay, what about now? Okay, it's going down. 93 point something, 91, 90. Okay, we're in the 80s now. Made it down to 79. 60 point something. So it's getting less and less. Started the biggest when it was the product of the two magnitudes when they were going the same direction, and now it's decreasing. See, it's decreasing as we go down further and further. What about, wait a minute, right there is a right angle. So still positive there, about 5. Still the key. Okay, now we got a right angle, pi over 2 radians, and look at that, 0. Now what happens as we go here? A little less than 0, negative 1.675. The angle is just a little bit bigger than a right angle. Okay, a little bit bigger still, right angle. Look what's happening. It's going down, down, negative 11, negative 15, almost negative 20. It's about negative 25 there, negative 33 there. It's going on down. Now we're in the negative, around negative 53 or 54, somewhere in there. Okay, it keeps going down. Negative 77, negative 78, negative 80s. Okay, it keeps going down. Negative 90. And what happens right? Negative, okay, we're almost there. That, I believe we're actually opposite each other again. And look what happens there. Negative 96. Keep going. Now it's going back up. So it looks like it goes somewhere between negative 96 and positive 96. The smallest it is when they're opposite. The biggest it is when they're the same direction, and halfway in between is 0 when they're at a right angle. So that's interesting, isn't it? See how that works? So let's go back to our slideshow and see if we can answer some of these questions. Okay. So how does the size of the angle between two vectors affect the dot product? If one vector is 1, 0, then what's the dot product? We'll go back to that in a minute. So the size of the angle, that's going to have something to do with it. Let's see, look at these other questions. If one vector is the vector 1, 0, then what's the dot product? What if it's 1, 0, 1? What's the dot product? If a vector is a unit vector, what do you get for the dot product? And then what if we increase it? So let's go back to here again and look at, so we're going to make one of these let's go back and make this a unit vector. Let's just go right 1 and do this 0. So that's just a unit vector going across here. Now, of course, when I do this, well, let's see what happens. That's just the vector 1, 0. So whatever the x component here is, that's going to be it. And by the way, that x component is the norm of this one times the cosine of that angle that they form. So it's just r cosine of that theta, which is that, and that's going to be the whole deal, right? So if I move this around, here times this, the r is not changing, but the cosine of that angle is changing. So that's having something to do with it there. Okay, so to make this 0, 1, I might want to switch this to pi over 2. That goes straight up now, so it's 0, 1. Now the angle between is a little harder, is not the same as just the angle from this one. But here we get, of course, just the second component of this, which is r times the sine of that angle. But of course, that angle is not the angle between the two vectors. And no matter what we do here, if we take this and lengthen this one, that's going to multiply. Like if we go from 1, which is about 4.2 here, to 2, it doubled. See? And 3, 4, it just gets bigger. So notice if I factor out the length of this one right here, the remaining part here stays the same, right? So it's just this magnitude times this amount, whatever that amount represents. So it turns out if the angle is 0, then the dot product is at the maximum, which is the product of the two lengths. As the angle increases from 0 to pi over 2, the dot product stays positive but decreases in size. The dot product turns out to be 0 when the angle is pi over 2, a right angle, 90 degrees, pi over 2 radians. As the angle increases from pi over 2 to pi, the dot product is negative and continues to decrease as it gets bigger and bigger until it reaches pi, and the dot product then is at a minimum, which is the opposite of the product of the two magnitudes. So if one vector is the vector 1, 0, what's the dot product? Well, it's just the x component of the other vector, just r cosine of the theta, and it's part of the other vector pointing in the same direction as the 1, 0. If the one vector is 0, 1, then it's just the y component of the other vector. It's the part pointing in the same direction as 0, 1. Okay, the length of that part. In general, if one vector is a unit vector, what's the dot product? It's the length of the other vector times some decreasing function of the angle between the vectors. So it has something to do with that angle. And what happens is if we increase the length of the one vector, it was the purple one just a minute ago, that's going to increase the dot product proportionally. So it looks like the dot product depends on the lengths of the two vectors and the angle between the two. So we seem to have something like this. A dot B, vector A dot vector B, is some function of theta times the norm of A times the norm of B. Right? But what about that function of theta? What do we know about this function? And once we find that, once we have that, see if you can find a function that has those characteristics that might be related to this. I've kind of given you a pretty good hint already what that function might be. Well, what have we known so far? We know f is decreasing on the interval from 0 to pi. It's the biggest when the angle is 0, and this f is just 1, right? So when the angle is 0, then this function is 1, and the dot product is just the product of the two magnitudes. It's the least at the other extreme when that angle is pi, and this is -1. So it's the multiply the two magnitudes and then make it negative. And when you get halfway in between at pi over 2, it's 0. So we need a function that starts out at 0, 1, goes down to pi over 2, 0, and goes down then to pi -1. Now, a straight line would do that, but it's not a straight line. Can you think of another standard function that fits there? Hint, also, we did one a while ago when it was pointing straight to the right. What was it? Well, hopefully you came up with cosine. Cosine function starts at 0, 1, goes down to pi over 2, 0, and then continues down to pi -1. And in fact, it turns out that this is exactly what we could do. So we could actually go back, say, to the GeoGebra applet and, oops. Here we go. And let's just check and see if that actually works here. Let's check it out with the calculator. So we've got, okay, so I've got the two magnitudes, 8 and 10. That's going to be, 10 times 8. And then we think it's times the cosine of this angle in between. There's the angle. I'm in radian mode. Let's make sure. Yeah, radian mode. And so I'm going to multiply that by the cosine of that angle. Okay. And of course that's rounded off, but that should be approximately what we got right here for this. 42.39 something. Okay. Some rounding, so there's not a perfect match, but it's very close. It turns out it is exactly correct. All right, so it turns out that if we want to do the dot product of A and B, which is here's A, here's B, we just multiply the corresponding components together and add them up. That's a pretty simple algebraic way of doing it. But there's also turns out to have a geometric meaning. It's also the cosine of the angle between the two vectors times the two magnitudes. It's actually pretty easy to figure out using this formula if you're given the two in magnitude and direction form, because you already have the magnitudes here and here. And if you have the two angles it makes with the x-axis, by adding or subtracting, you'll be able to figure out what angle is between the two. Just do a cosine of that and you got the whole thing there when you multiply. Whereas if it's in component form, this component definition works really well. Another thing that this allows us to do is take this version right here and solve for theta. Okay, divide by both norms. So you've got the dot product divided by the two norms like this. And then you got cosine theta equals that. So then you do the arc cosine or inverse cosine of both sides. And so theta is the arc cosine or inverse cosine of the dot product over the two norms. So if you've got it in component form, you can figure out what the numerator is pretty straightforward. And then you can figure out the norms and then do an arc cosine. Remember, arc cosine always gives you an angle between 0 and pi, which is appropriate for measuring sort of the smallest positive angle between the two vectors. Okay, so for example, let's do a 3D version. The angle between vectors 1, 2, -2, and 3, 0, 4. So we do the dot product. 1 times 3 is 3. 2 times 0 is 0. -2 times 4 is -8. Add those up to get -5 for the dot product. And then we do the norms of the two things. So this is a square root of 1 squared plus 2 squared plus -2 squared. That's 1 plus 4 plus 4 is 9. Square root of 9 is 3. And then this one is 3 squared plus 0 squared plus 4 squared. That's 9 plus 16 is 25. Square root of 9 is 3. Square root of 25 is 5. So that's 15 in the denominator. 15 and 5 cancel down to 1 over 3. It's negative. So it's the arc cosine of negative 1/3, which, by the way, is really the only way you can really say it exactly. But you can get a decimal approximation in radians or degrees out of your calculator if you want to. Okay, moving right along. Here's a proof that the dot product formulas are actually equivalent. Okay, and the following proof is going to make use of the algebraic definition of the dot product, the definition of the norm of a vector, some basic algebra, and the law of cosines. So I'm going to do it just for 2D vectors, dot product, but it works very similarly for 3D, 4D, and so forth. Okay, you could write it out for in general for n dimensions. It really wouldn't be a lot different than this. But so here we have A and B vectors, and theta is the angle between. And this vector going across here is A minus B. So notice if you start here, go to B, then go across A minus B, you end up at vector A. And so that means if you add these two together, what do you get? Well, the B's cancel, so you do get vector A. So there's a picture. Now you probably remember the Pythagorean theorem that says the hypotenuse square is the sum of the squares of the lengths of the two legs, right? The lengths of the hypotenuse. Okay, so you've got this norm equals this side square plus this side square. Well, that would be fine if this was a right angle here. But if it's not a right angle, the law of cosines gives you an adjustment for that. You have to add this extra term. If you call this guy A and this guy B and this guy C, you get C squared equals A squared plus B squared minus 2AB times the cosine of the angle opposite side C, which is theta in this case. Okay, and so again, it's this norm of this side here. It doesn't have to be the hypotenuse, just some side, equals this side square plus this side square minus 2 times the lengths of these two sides times the cosine of the angle in between. That's the law of cosines. All right, now what is A minus B square? Well, A minus B is A1 minus B1, and then you want to and then the comma A2 minus B2, and we want to find the norm and square it. Well, the norm says square each of those things, A1 minus B1 square plus A2 minus B2 square root, but then you want to square it. So the square and the square root cancel. So that's how we have this. Similarly, the norm of A square, the square and the square root cancel, so you just get A1 square plus A2 square. The norm of B is B1 square plus B2 square. And I'm going to just leave this alone, minus 2 norm A, norm B, cosine of theta. Now, if you notice, let's see, I'm going to leave this side alone, just drop these brackets, grouping symbols. Over here, I'm going to square this out. So you could use, the distributed property, FOIL, whatever. So you square the first term, A1 square, square the last, it's plus B1 square, and multiply to double it for the middle is negative 2 A1 B1. And similarly, this one's A2 square minus 2 A2 B2 plus B2 square. All right, so it's getting a little messy, but what we do is we notice that both sides have all four of these things here. See, so that one's going to cancel out with that. This one's going to cancel out with that one. This B1 square is also going to cancel out with this one. And this one is going to cancel out with this. So if I add all the opposites to this, not only does that go away, all these go away except for these two terms right here. All right, things are starting to look up. Divide both sides by negative 2 and distribute on the left. The negative 2's all go away. And wait a minute, look at that. Isn't that exactly the dot product? A1 times B1 plus A2 times B2. So sure enough, the dot product really is the norm of A times the norm of B times the cosine of the angle in between. Now it turns out that this has something to do with what's called a projection. Okay. Okay, so now we have these two definitions, right? Or two different alternative representations for the dot product. One is given by this algebraic definition, and the other is given by this geometric interpretation, cosine of theta times the product of the two norms. But another thing that we can do that's useful is to talk about projections. So in the GeoGebra app, we're going to click on this projections thing. And notice what comes up here is you have you take this red vector and break it down into two components, not necessarily an x and y component, but a component that goes in the direction of the purple vector and one that's perpendicular to it. And we see that it's the part that goes in the same direction that makes a difference. So we can think of this as shine a light that's going perpendicular to this purple vector, and the red vector then casts a shadow. The shadow gives us this brown vector right here. That's called the projection of the red vector onto the purple vector. So it's the projection of, well, the red one's U and the purple one's S. So it's the projection of U in the direction of S. So the thing that's casting the shadow is the one in the parentheses, and the one that where the shadow falls is the one that's the subscript. So the projection of U in the direction of S. And that's going to be that vector. Its length is called the component of U in the direction of S. So here's a question for you. Can you come up with a formula for the component here, that length? It could be negative if it's pointing the opposite way, so a signed length. Well, let's think about it. If this angle theta is the angle between, it's labeled alpha here, but let's call it theta, then what do we have? We just have a right triangle here. Remember your basic trigonometry? The cosine of that angle is the adjacent side, the length of the adjacent side, over the length of the hypotenuse. And if it's pointing the opposite direction, it still works out the same. You just use the cosine of the obtuse angle, and which will be negative. Okay, so anyway, what is the component? Well, it's so it's adjacent over hypotenuse. Well, the hypotenuse is the length of U. That's the norm of U. And then times the cosine of that angle theta is going to be the size of this guy right here. And it will work out correctly as a negative if it's going the other direction, a positive if it's going the same direction. Okay, so now if we were to take this and multiply this by let's see, if we take the cosine of theta, we can replace that by the dot product divided by the two norms. See right here? And the dot and these u's cancel. So one way to get the component is, there's two ways here. You can take the size of u times the cosine of the angle in between, if you know the angle. If you don't, if you only know the two things in component form, compute the dot product this algebraic way, and then divide by the norm of the other one here. Now the projection of this is actually a vector, okay? So remember a vector, remember scalar multiple? If you take a vector that's a unit vector in a particular direction and then multiply that by its magnitude, you get a vector going in that same direction that's the right length. So if we want to find the length of this projection, we need to multiply that component, which is its magnitude. See, the magnitude of the projection is the component. Then we want to just take that and multiply by a unit vector that's going in the same direction as s. Well, to do that, you just multiply by the vector s divided by its own norm. Okay, if we put these constants together, we get u dot s over the size of s squared. Or another way to get this size of s squared is just to do s dot s. So look what happens if these are both, if this is A1, A2, A3, and this is also A1, A2, A3, this becomes A1 times A1, that's A1 squared plus A2 squared plus B plus A3 squared, or so forth. So what happens is, that's just exactly the same thing you get under the square root for a norm, and then that square cancels the square root. So another way to write this would be a dot product of the s there with itself. Okay, so there it is using that formula. Okay, so let's go a little bit more and say, can we think of this as an area? And yeah, it actually can be thought of as an area. So here's a picture here. So the dot product has something to do with the component of the first vector that's going in the direction or the opposite direction of the second vector. And here's look what happens here. It turns out to be the size of this guy times the size of this the component, the size or the magnitude of this projection, times the magnitude of this one that's the second vector. Well, if we take this this component and rotate it 90 degrees, we can make a nice little rectangle. So this side right here is the same as the length of this projection here, the absolute value of the component. And if you multiply those two lengths, you get, well, the area of this rectangle, which turns out to be the absolute value of the dot product. Again, if the two vectors are going the same direction, you get a positive dot product. And if the two are going the opposite direction, you can get the same, say if I rotated this guy around going the opposite direction, but the same length, we'd get the same size of rectangle, but it would be a negative for the dot product. Okay. Now, we know that the dot product is commutative. It's real easy to see in the algebraic sense. Here's something that illustrates it in the magnitude and direction sense as these rectangles. Now, if you're doing the dot product the way I've done it, and you think of the red one as the first and the purple as the second, you're projecting that down here, and we get this rectangle down here, which you can see its area, which is the dot product. But if you take it going the other direction, you want to project the purple one onto the red up here. Well, if you do that, its projection, where you're projecting this way, right? And it gives you this little purple vector here. Also gives you this normal or normal, orthogonal, perpendicular, three words for the same thing. That component going that way, but the one that's going in the same direction is this. Rotate that around, it gives you this rectangle. Now that's a different dimension rectangle, but it turns out to always have the same area as the other one. And so that gives us that setup. So seeing that in the picture here, you can look at the projection. Well, yeah, I can look at the projections and the area, and you can see how that changes as we rotate this around. Again, let's just maybe put this somewhere. That rectangle is going to be the biggest when I can get these guys going, if I can get them going, in the same direction. That's 80. That turns out to be the biggest. And that rectangle is going to get smaller as we go away. It disappears altogether if you get them right angles. And when they're pointing against each other, you get an area here, but the dot product is going to actually be a negative number, the opposite of that. And here it is sort of worked out in component, two norms, which are given by here, so we know what those are. And then the angle between you can find by just working with these, in this case subtracting the two to get the angle between, and do the cosine of that, and then work it out that way. Of course, the two norms are always positive, but the cosine could be positive or negative depending on whether it's acute or obtuse angle. Okay, now if we switch the order, we get this here, and again, depending on what's going on here with the angles, these could be considerably, noticeably different, different size and shape of rectangles. Like you can clearly see, those are different rectangles, but it's the same area of the two. This area, there's a lot of numbers here, sorry about that. But here the area is right there, and the area is right there, and those are both the same, well, as the absolute value of the dot product. Now, by the way, you also have this one allows us, this particular app allows us to enter in the component form. So I could have done by choosing these to be natural numbers by doing the sliders, I can basically do the same thing that were in Mr. Brzezinski's app that we looked at earlier. And these can be moved around, but really you would rather them be, the tails together, and this puts them in standard position, so it's always at the origin. Here you can look at the components. We can also have it compute the magnitude and directions there. And then we can look at the components in the direction there and look at the two different rectangles again. So we can do a lot of the investigations in either way. All right, so I think that's a pretty good introduction to the dot product. We got an idea of how to compute it algebraically, how to compute it and see what it means in a geometric sense. And it tells us something about that angle in between two vectors. So now we know how to find the angle between two vectors. And we can do a few things with the dot product. Hopefully have a pretty good understanding of what's going on with that. We'll move on to the cross product in our next video.